Okay, so let's review what we learned so far. So start with the layering. Why is the layering is important? Because the programmer or the any designer doesn't need to understand full stack, but only need to understand the corresponding stack, encoder and decoder up and down. That's it. Simplify the problem. Therefore, it can evolve by focusing on that project, on that time. Okay, so whenever we're building the application, we don't need to worry about everything. And when we talk about security, is encapsulated, also encrypted per layer. So it is different to, it is very hard to decapsulate it without the information and open the information until you need it, okay, with the permission. So this is a basic layering concept. We talked about this OSI 7 layer. Why OSI 7 layer? Long time ago, people thought, okay, layering concept, I'm buying your layering concept. So how many layers do we need? At the time, they thought the 7 layers are adequate, and they made a decision. Okay, 7 layers. We're going to OSI the standard by the network guys, and okay, this is the layers. So 7 layers from lower the physical, the higher the more abstract. So the in the middle, the routers and switches are only take care about the second layer when you are switch, up to the third layer when you are routers. And that is how we design. But in reality, it is more like this. So we call it internet architecture. So this is also broken because of the Chrome these days. We don't know where it goes to, but it's more simplified and less layers are used in the field. Okay. Then we talked about the performance, how we measure the performance. We talked about what is byte, what is a bit. You have to synchronize your metric. And we talked about the baud rate. Long time ago, baud rate and BPS was same, but now we are evolved in the symbol rate. Symbol rate meaning whenever I talk to once, long time ago that once was 0 or 1. Whenever I talk to once, it was 0, 1 or 0, 0, 1, 0, 1, 1, 4 of 1. Therefore, because the receiver has more sophisticated, then they can decode it properly. So the baud rate changes to, the concept of baud rate changes to the bit rate. So we talked about how we calculate the total transmission time by synchronizing the metrics. And we talked about all these possible cases. And I think it is easy to do. Then we talked about what is important for latency or bandwidth. It depends on your application. Okay, your application require sensitivity, something like the live streaming, the latency is more important. But if you think about the more file over time, when bigger file, higher definition, meaning that the bandwidth is more important. So we talked about bandwidth and delay product. So in the pipe, how much are there? Okay, something like this. And we talked about the real world delay and RTT and bandwidth. And all we talked about, also we talked about the right application and how we calculate the bandwidth required for the given video streaming. So the video streaming is one of
Professor.
Question? Was it a question?
Yeah, can I ask a question regarding the packet sending? When we go back to the slides where we were calculating the sending of packets with different situations.
This one?
I think it's slide number 12.
Okay. I'm at the slide number 12.
Oh, okay. I have a question. Why the number of packets is 1,536? Isn't it just 1,500? Because in 1 megabyte there are 1,000 kilobytes, right? So we are calculating per kilobyte.
So okay, go back to the point. So in computer science, when you talk about 1K, which is actually 1,024. Clear?
Okay.
Okay, so So in computer science, when we talk about the 1K byte, actually 1024 byte, this is typically what we are using. Why do we do this? Because we are built up from a binary. Okay, 2 to the power 1 is 2 to the power 2 is 4, 2 to the power 10 is 1024. Clear? Then why we then why we using this as 1024 means number of packets I have to, because my packet size 1 kilobyte and my whole file is 1.5 mega. Okay, so if I divide it by 1 kilobyte to 1.5 mega, which is 1000 different. In the computer science field, it's 1024 different. Clear? No?
Okay.
Oh, no. So I thought the this top. Oh, okay. So back to here. So I have to send 1.5 M, and my size is 1K. Okay. Divide by this. Divide by 1K is K is gone. Then it becomes K, right? So where's this K means? Rather than 1000 in computer science, we are using 1024. Why? Because we are based on the binary. No? Not clear?
Yep, clear.
Okay, so we talked about this, and we talked about network jitter. So to prevent the jitter, we have to buffer the video ahead. So how you calculate the buffer, the concept. So we divided the, if you remember this, every second, 1, 2, 3, 4, 5, 7. Then this means 50 milliseconds per frame, meaning for 1 second, you have to have 1.5 seconds. So your video is buffered 1.5 seconds, 1.5 seconds. Then we play with this, right? If you remember. So we have a video on this, then you can check it if you want. Then we talked about encoding and framing. Why the encoding is necessary? Because we are using this in a typical communication. We are not just sending 1010 binary. Sending 1010 in a plain binary is very susceptible to error. Therefore, we have to do some tricks to prevent error. If there's something happen, I want to have an ability to recover properly. Okay. Then we talked about the basic term, the baud rate and BPS. We also talked about the Shannon's theorem and Nyquist theorem. Those are the two geniuses who defined the upper limit of the communication, and we human never reached it yet. Okay, if you can reach the theoretical limit, then you can sell your idea to the company, then you could be a millionaire easily. Okay, so today, a long time ago, the basic, the scheme was talked about. Why is the Manchester coding is needed? Just sending 1, 0, 1, 0 is not clear. But as we applying our clock information to the coding mechanism, it's much easier and more stronger to error, more immune to error than NRGI. Then we talked about the 4B, 5B encoding. Why necessary? Because some of the patterns are very similar to, very susceptible, like a 00005, 5 times a 0. What is this pattern? Okay, something like this. So we have to eliminate those patterns. Then we have to have some overload. Then we talked about framing. Why the framing is important? Because whole packet cannot be delivered in one frame. I have to fragmentize it, smaller. Okay, whenever I lost in one frame, then I can recover that targeted frame again. Okay. Then something bad happened, we have to have ability to correct it. At the very basic one is detection of the error. So we checked with the error detection with the parity, 1 bit. So if there's something bad, I have ability. Is it correct one? Is it no? When it is 1 bit error, okay? And we have a more ability if we have two-dimensional parity. Then we have, by this, we have ability to detect 1 to 3-bit error and up to 4-bit error when we are lucky. And we have ability and 1-bit error correction when we know, okay, there is a 1-bit error occur. The overhead is large too. So we also talked about the CRC, and we did our homework on the CRC. And when you practice and how it is working in the code-wise, in a more complex one. So we talked about how you confirm your CRC by checking and dividing, and if the remainder is existing, then there's something bad happened. Okay. So when we're sending the information, we always make sure the remainder is not divided. So if you know, so this is my actual information, and this is my code, and this is actually transmitted. If this packet is transmitted, then I'm dividing with this code. If there is a remainder, meaning there was something wrong. If not, it is correct. Okay. So CRC is very practical. In a CRC32 is commonly used in today's technology. With this 32-bit, we have ability to the megabyte of the file size. So we also talked about the Hamming distance, and we have ability to decode properly when it is contaminated. Okay. So we talked about Hamming distance, right? Okay. So no answer.
I have a question on the previous slide. Can I ask you a question right now?
Sure.
Like what is the N and K of Hamming code? Like in the previous slides.
This one, N and K code. So let's see, this one is 1, 2, 3, 4, 5, 6, 7, 8. 8 messages. That is N is 8. So K is how many? 1, 2, 3, 4. 4 is my K. So it's I consistently use the N and K, even with the parity. So this one, N is 11, K is 1. In this one,
I'm getting a sync error from your Zoom, so I can't really read what you counted.
Okay, so N is message, K is your redundancy.
Like N is the message with the remainder added, right? Is it? Or...
Yes. So if you look at the two-dimensional parity, are you seeing the slide number 6?
Yes.
Okay, so in this one, my N is 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. My N is 35. How many K do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13. 13 is my K. Your redundancy.
Oh, so is K. The redundancy added is the K, and N is the total message count.
Yeah, right? So all the encoding and decoding. So N is your messages, length of your message. K is your redundant the bits for the error correction or error detection.
Got it. Thank you very much.
Okay, so the main design should be K is very small compared to the messages. Good. Okay, so I think we did Hamming 2. Let me start with the reliable transmission. Okay, so today we talked about reliable transmission. What is reliable transmission? So by far, we talked about what is 100,101 in the lowest layer. We call the layer 1. Now we talked about layer 2. Okay, so let's say I have ability to correct error or detect error. Okay, so reliable transmission is basically on Do I need to retransmit or no? Okay. So reliable transmission, there is a two different type of communication. One is lossless, the other is lossy. Lossless is there is no error in your communication, which is close to the theoretical. And your wired and your fiber optics are very close to lossless. That is why we use in cross-country in your fiber optics. But lossy communication is like your Wi-Fi. It's very prone to error. Okay, the one more term is simplex connection. Simplex connection is the antonym for simplex is duplex. Simplex is one is talking, the other silent. The other is listening, then everybody's silent, then the other is talking and one is listening. So one talk, the other silent, the other talk, one silent. Okay, there's one direction. Then we call the simplex. Duplex meaning while I'm talking, I have ability to listen. That's a duplex. Simplex is while I'm talking, I have no ability to listen because I am overwhelmed by my speaking. When I listen, I have no ability to talk. Okay, in a very fine time level. Fine time level because we are using the communication data link. Okay, so simplex connection. Now we understand what is a simplex connection. One talk, the other silent. Simplex stop and wait, meaning if I talk, I'm waiting for. If I receive some feedback, oh, your connection was clear and I received your message clearly, then I can start talking. Meaning stop and I'm waiting. How was it? How was it? Okay, that is stop and wait. In the lossy communication, it is more complex. So process of retransmitting frames cannot be corrected by the CRC code, meaning I have to retransmit. Okay, and stop and wait. Oh, I understand what is a stop and wait. Go back and selective repeat. Then we talked about go back and selective repeat in this slide. Okay, so the simplex protocol and lossless channel. What do I do? Data flows only one direction, which means I'm using simplex. Communication channel never lost frames. Receiver is always ready to receive. Problem: receiver can be flooded if it does not process the packets fast enough. Meaning, I'm listening. Okay, I'm listening. I do something. I do decoding. But if I'm overwhelmed, I have ability to listen from one guy, but if two people are talking to me at the same time, or three or four, if the message is too many, if that guy is talk too fast, meaning I'm overflooded. Okay. So solution is delay at the sender. Why do we need a delay at the sender? Okay, I'm receiving. Okay, next. Okay, what's the phone number? 3631. I'm saying 631. Then I can say that. Okay, that's the power of delay that we're going to talk about. Okay, so let's look at the simplex protocol, sender and the receiver. So we always need 2 times of the connection setup. Hey, can I send you? Sure. Okay, I'm going to send in this way. Okay, I got you. I'm waiting for. Then I'm keep sending it. I have ability to keep sending because receiver has ability to digest properly and the channel is not lost. Okay, then let's do this. So simplex protocol and stop and wait. Hello, my phone number is 631-438-2424. Okay, oh, your message is corrected. Yes, okay, then this is basic stop and wait. After I'm sending it, I stop and I'm waiting for time until I receive feedback, which we call acknowledgement. Okay, so let's say I don't have a proper timeout. If I'm waiting for a long time, meaning it could be delivered, or this egg is not delivered properly, or this message wasn't delivered properly. So he will not send, or it will be lost in the middle, meaning I have to wait forever. So I have to have some threshold. What if this time is too short? I sent the messages, then the receiver sent it again, but my patient is too small. The egg is coming after my threshold. Then I have to have clever mechanism to find the timeout, tighten up, and long enough. Okay. So the 2 possible cases: if the frame was sent in the middle, the receiver doesn't receive, so they don't send it. and waiting for timeout, then send it again. How? Okay, there's a basic strategy, and stop and wait. Okay, okay, failure of the stop and wait, two possible cases. So lost, the receiver sent, but in the middle it is not properly delivered, or your timeout threshold so tight, then it passed your timeout. Okay, so solution based on the sequence number. How can you solve this problem? Let's talk about how can you solve this problem. So I'm gonna pick $14. Okay, let me. Okay, I'm gonna pick the Yu Jung-min, Son Ye-eun, and Pan Kelly. I think Pan Kelly has dropped the class. And I'm gonna pick the Jung Ho-jin. Okay, so what's their strategy? I'm gonna start with the Jung-min, Yu. Okay. What's
I'm
their
not sure.
Yeun?
Professor, I'm forming you, but I'm not sure, so.
Okay, so Yeun? So we have a failure cases of stop and wait. How can you overcome this scenario? Yeun? Son, Yeun. Okay. I think that Kelly Pang dropped the class, isn't she? There's no Kelly. Okay. Then Jung Ho-jin?
Maybe. I'm not sure too.
Try. Don't worry.
Maybe increase or decrease the amount of timeout a little bit.
You have like more dynamic timeout.
Yeah, dynamic timeout. Yeah.
Okay, something like this. Okay, thank you. Anyone else? Nobody? Are you guys still in the bed?
Can we have
Okay.
sequence number for each frame?
Great.
And, like, ACK.
Okay. Who's this speaking? Ulbeck?
David.
Samar?
It's me, David.
Oh, it's David. Okay. Great. David was right. So we have so if I'm sharing the screen with you, so whenever you speak, stupid or no, and crazy idea, I'm always love to hear. Okay. So whenever comment on this, you will get some attendance point. If not, I'll keep asking you. I'll keep asking because I'm sorted based on the your attendance score. Then I'll always start from the lowest score first. Okay. All right. So what's the issue in here? So what's the issue in this case? Oh, frame was sent, and egg is coming after. Frame sent it again, and egg is coming after. I wasted whole information, right? So to solve this, we call the sequence number. So let's start with the simplest one, 1-bit sequence. 1-bit sequence is this either 0 or 1. So ideal, frame 0 is sent, okay, x0 is received, okay, now I can send 1. Frame 1 is sent, and egg 1 is received, okay, good enough. Now I can send 2, which is in the frame sequence, I'm 0. 0, 1, 0, 1, 0, 1, in the view of the frame number. In the view of the sequence number. I could have long sequence number, but it also takes up the longer header. Clear? So I want to minimize the header, minimize the K, minimize the redundancy. Then I want to guarantee the proper communication. Okay, so start with the 1 bit, 1010. Then, oh, it is working. What's the issue with the 0 and 1? The simplest the sequence number. Let's say I sent the 0. Okay, so it is not delivered properly, so I sent the 0 again. Because my threshold is over. My timeout happened. So I sent the 0 again. Oh, I received the ACK for that. Then I'm sending 1. So 1 is, this guy is cleared by this point. Okay, now I'm sending this guy. I sent this guy, and ACK is delivered. Okay, so 1 is actually missing, but I received the ACK. Oh, then I move on to the next one, and 0 again. Okay, that is not good, because which ACK do you mean? The simple ACK? No, if you look at on the left, I have 0, the ACK also has a sequence number. Okay, simplest one, it's not working properly, it has a very low threshold problem. So ACK should be specified. So ACK on which frame? Okay, therefore, our communication evolved in this way, and we have a more complex sequence number scenario. So if I show you this, so sequence number, so in the page 15, sequence number could be much longer. And in an example, I'm only using 5. It could be, it usually up to 128 in the LTE communication. So let's see. Oh. Let's see, efficiency of the stop and wait. Inefficiency of the stop and wait, okay? So I have 1.5 megabps link and 45 millisecond round trip time, which is my latency, and which is my pipe speed. So delay bandwidth product is 8 kilobyte, which is 1.5 M multiplied by 45 millisecond BPS, right? Oh, second gone, M become K, M is gone, and if you multiply these two, it is 67.5 K bit, right? KB, right? Therefore, in the view of the bytes, it is about 8 kilobyte. Why? I just divided by 8. Okay. So if the frames are 1 kilobyte long, then the max rate is I have 1 kilobyte converted to the bits, divided by my latency, then my max rate is 182 kbps. Okay. My link is 1.5 M, but I'm only available to 182K. Therefore, my efficiency is at 12%, which I'm only using 1/8 of the capacity. Okay, my goal is keep the pipe full and have maximum number of the unacknowledged at any given time. So let's see, do you understand this concept until here? Okay, let's do this again. So my link height is 1.5 Mbps. My delay is 45 milliseconds. So what's the my pipe? How much is in the pipe? My pipe meaning my speed multiplied by delay. In this case, 1.5 Mbps multiplied by 45 milliseconds, which is second gone, because it is per second. M gone, then K. I only have K and B, 1.5 and 45, which is 67.5 K B K B. If I convert it to bytes, I do divide by 8, then it is about 8 kilobyte. Okay, so my pipe is 8 kilobyte, and if your if your frame size is 1 kilobyte, meaning I have ability to up to 8 kilobyte, but I'm only using 1 kilobyte. Okay, do you experience the delay? Oh, really? Okay. My voice and screen has few seconds of delay. Ah. Okay, so let me disconnect my iPad. Okay. Hello. How about now?
We can hear you, but we can't see your screen.
Okay. Can you see my screen? Okay, let me try. So I just want to type hello, Hello. Can you see my hello? How long? Not yet.
Where is? Oh,
10
it's
seconds.
yeah.
Oh.
It's a.
Wow. Hello. Now yes, meaning annotate. Hello. One, two, three. It's gone now, meaning the latency is gone. Okay.
You're in the first slide right now on the screen.
Yeah, hello is gone. Okay. Okay, I'm checking the the delay. So by checking 1,
1, 2, 3. We just saw like 1 second ago.
1 second.
Yeah, like 1 second ago.
Okay. All right. Then I think it's better. So I'm gonna disable the.
So I meant like after 30 seconds, we could see 1, 2, 3.
30 seconds.
Yeah, I counted like it was like 30 seconds or so.
Or 15 seconds. Seriously. What's the issue? I'm using a wired communication. Okay, let me try one more time. Hello. 1 second. Seconds. That is no good. So 1, 1, 2. How about now? Hello.
I don't
Hello.
see our screen yet.
You don't see my
The
screen?
screen just showed up.
Just showed up.
Ah, you showed up my screen. Oh, my computer has an issue.
Maybe it's queuing delay.
Okay. So I think video is fine. Oh, resume the recording. So my intention in here. So do you see my slide? Slide number 7.
No.
You're still on the Note app on your iPad. Oh, it doesn't.
Now it showed up.
Okay. So I'm going to show you my intention. So I want to talk about the efficiency of the stop and wait. You guys understand what is stop and wait? Stop and wait meaning, because I have a simplex communication, I have to wait until I collect the feedback. So I'm calculating a stop and wait's efficiency. Okay, clear so far? So my link is 1.5 Mbps, and my delay is 45 milliseconds. And my delay by bandwidth, delay and bandwidth product is 8 kilobyte. And if the frame is 1 kilobyte, and I have the pipe with the 8 kilo, which is I'm only using a 1/8 of the my pipe, right? So in calculation, if I'm sending a 1 kilobyte in the 45 millisecond delay, so I'm using is 182 kilobps, and I have a link of 1.5 megabps, which I'm using 12%, which is equal to 1/8. Okay, so how can you solve this issue? How can you make, or how can you utilize, how can you improve your utilization? Do you understand what the question is? So I want to improve the utility of this function, stop and wait, because it is so inefficient. So how can you make this more efficient? Okay, so I hope everybody understands the point. So go back to the point. Okay, David said, can we send the 8 frames ahead of time? Okay, great point. Anyone else? So are you seeing my CSE310 attendance sheet? And no? Okay.
No.
You'll see about, still on the slide. I switched to my computer, and it's showing attendance sheet of the 310.
Now we can see.
No, you can say, okay. Popped up. Okay, so if you look at it here, I checked everything you marked in the class as 0.5. The top is 1. So I'm always picking the lowest score first. That's why I keep asking you Jungmin and Yeun and yeah, 2 of you. And if you skip, then I'm gonna keep asking you from the lowest score again. Okay, so Yeun and Jungmin, any strategy to make this more efficient? Okay, Yeun. So how can you overcome this inefficiency? You can raise your voice. Okay, you will see a slide again. I switched to the slide about 5 seconds ago. So how about this? I will upload my slide before the class start. I thought the giving you slide is more efficient because you guys can focus on the slide and focus on the lectures. Then we have some technical issues. Then I will make sure I will upload the slide ahead of the lectures. So can you see the slide now?
Yes, okay.
Okay, Yeun, what's the strategy? And Yeun and Jungmin, Jungmin, the wider bandwidth. Okay, let's say your environment is all fixed. So you have to have the in the software way, your the policy way.
Maybe make the connection to be able to send packets and also be able to listen at the same time. So
Okay, good point.
like the
Anyone
same
else?
that you showed us, like like not like send, wait for response, send, wait for response, but like just send, and another instance will just like.
Okay, great point. So the you Ulbeck, right? This is
Janar.
Ulbeck, right? Janar?
Yeah, Janar.
Thank you. So another point is the point of this. What's the point of this? So before act, I want to send it. Meaning stop and wait. You have to stop and you have to wait for the feedback. But you know what? One feedback every frame that I send is not necessary. Maybe I can send more than I can expect periodical feedback, not every feedback. How about that? Right? I think that Janar is explained to that. You don't need to have every frame and every feedback for that frame. Rather than doing this, I can have periodic feedback. If something goes well, I don't need feedback. If something bad happened, I want a feedback. Then I can go back to the point and transmit again. That's the right approach I expect. That's what I expect. And Janara, thank you. And Jungmin, and good try. And so basic strategy is to live up to the end frame on acknowledge at any given time. Meaning, I sent the messages and waiting for the feedback. Oh, just waiting for the feedback is not efficient because I have to wait every package that I send. Don't do this. I'm sending end frames unless it is specified. I only need a periodic feedback. when something goes well. If not, I don't need your feedback. Okay, so I only need periodic feedback. Then I can save the listening time, meaning I can make unacknowledged frames long enough. Okay, that is the go back and protocol. Previously, the stop and wait protocol. Now I can do a go back and protocol. Okay. So go back and protocol has a multiple terminology. We have SWS, LAR, LFS. All these things are related to the buffer size, buffer on the sender side, and buffer on the receiver side. So, do you see the page number 10? So just ping me one when you see the page number 10.
We can see
We
page
can
number
see it.
10.
No?
We can see it right now.
Okay, thank you. So, okay, so sliding window depicted in like this one. So I have to have last acknowledged receipt and the last frame sent, meaning I am a sender. I'm keep sending my messages. I have to collect a periodic feedback. Okay, so last frame sent and last acknowledged receipt. But I have a limited ability because I cannot send 1024 at one time because I have to feedback periodically, meaning I have some limited information, which is my window size. Okay, so rule in here in the go and back, I have the size of SWS, send window size, meaning so whenever I acknowledge, I can release them, and I can send more. Let's say I have size of the 7 window size, and I can keep sending 7, and whenever it is acknowledged, I can release it, and I can send it continuously. So your rule is your window size is always smaller than LFS minus LAR. LFS is last frame sent, and LAR is last acknowledged receipt, meaning your buffer size. Okay. On the receiver side, RWS meaning receive window size, and LAF is last acceptable frames, and last frame receipt, and LFR last frame receipt, and you have last frame receipt, and you can continuously receive, but you have a buffer. Okay, whenever your frame is received clearly, I can clear it out, and I can digest this much. I can digest this much without feedback, which is your receiver side. So RWS is receiver window size. You make the receiver window size always smaller than LAF minus LFR. Okay. So you have to update your value every time when there is feedback or no. Then this is what we use. Okay. So I'm looking at slide number 12. It will take some time for your feedback.
Professor, I have a question. So is SWS and RWS like a buffer?
Yes,
for
buffer
each
size.
size?
It is precisely, yes.
Okay.
So are you seeing slide number 12?
Yeah, we can see it. I can
Okay.
see it.
So it is a basic go back and protocol. My sending buffer is a 4. My receiver buffer is 4. Okay, that is a good size. But I'm simplified to the SWS of 4, receiving size 1. So my buffer on the receiver is very small because ability on the receiver is unlimited. So what do I have to do? Sender can keep sending 0, 1, 2, 3, 4. Okay, so sender has ability for sending 4, right? So 0, 1, 2, 3. Receiver has ability to receiving 1, right? There is no buffering concept because you only have RWS as 1. Then LFR, send the feedback, then sender can send the 4 again. Okay, but the packet 1 is not delivered properly and it exceeds the timeout. Therefore, I'm keep sending again 1, 2, 3, 4. Okay. So when the packet 1 is not delivered properly, then I have to keep sending 1, 2, 3, 4 again. 1, 2, 3, 4 again. What should we do? I have to increase receiver's ability. So in this case, receiver's ability is more important than a sender's ability. Clear? Receiver have to have ability to digest properly. Then sender can send. So go back and protocols example in the piggybacking. Piggybacking is basic duplex communication and attach ACK on reply frame. Meaning I don't make the specific ACK, but if there is communication I'm appending ACK on the tail of the ongoing transmission. So I'm looking at page 15. Okay, this is selective repeat. Do you see page 15?
Yes, we see it.
Okay, so example of the selective repeat meaning, I have ability to buffer it. Okay, my receiver side is buffer 4, sender side is buffer 4. So I'm keep sending 0, 1, 2, 3. Oh, I received the feedback from receiver, 1 is clear. Then I can send it 4, right? Then the timeout of the 1 happened, so I have sent 1 again. Okay, then 2, 3, 4 was awaiting, which was buffered on the receiver side, and 1 is solved. So sequentially, I was waiting for 0, 1, 2, 3, 4. 0 was clear because I sent the WAC, sent the ACK. 1 wasn't properly. 2, 3, 4 was received, but it's not the one that there is some missing peak. Then I'm waiting for the 1 sent again. Oh, I received 1. 2, 3, 4 was buffered, so I naturally solved. So at this time, I'm sending ACK for 4. Then the sender keeps sending 5, 6, 7, 8 sequentially. Clear?
Professor?
Yep.
So the receiver does not have to send all the ACKs for the buffered
Clear.
frames.
So it's a periodic. So whenever you receive 1, 2, 3, 4, if you're sending 4, meaning until from the start till the 4 is fine. That is the strategy of the ACK. If you're sending ACK for 100, then until that point 100, everything was good.
So if there isn't problem from like for frame 3, like for example, receiver did not receive frame 3, then would it just send only up to 2 once it receives frame 1?
Oh, I'm sorry. So can you send it again?
So like for this, like for my case that I just mentioned was that so receiver sent ACK for 0, and then the buffered are like the sender sent up to 4 frame, and then if the frame 3 was not received by the receiver, then would the receiver send ACK up to frame 2?
Yes.
Okay.
Then the timeout happened on the sender side because I didn't receive the ACK for corresponding packet. Then the sender will automatically send the third packet.
Got it. Thank you very much.
3, 4, 5. Okay. Okay. Any question? So difference between the selective repeat and go back N is I'm receiving out of order packets. Clear? Because the 2, 3, 4 was buffered. That the power of buffer on the receivers, it gives me ability. I have ability to accept the out of order packets. So ability to the receiving and the sender, if we have multiple sender, then receiver's information is more important. When there is a one and one sender and one receiver only, then making receiver buffer bigger than the sender size doesn't make sense because there's only one receiver, one sender and one receiver, okay? But in reality, we have more senders in a given environment than a receiver, so making receiver buffer bigger always better performance, okay? So I want to quickly start at the lecture 7. Do you see my new slide?
Yes.
Okay, so MAC is multiple access protocol, meaning previously we only assume one sender, one receiver. Now everybody wants to share the medium. Okay, that is a MAC. There is a multiple access. So multiple people want to talk to me. Okay, so the strategy for the channel allocation problem is how to share access to the common medium. So let's say I'm talking to you, 15 of you. Let's say we are in the classroom. If everybody want to ask question about the topic, then what should you do? We have to pick the guy, and you may start, and you may start. So we have to share the medium. In that case, medium is our air, because our voices travel over the air. In the communication of the wireless, air is medium, and the communication is wired. That your wire, fiber optics, or the landline is your medium. Then how can you share your medium properly? So we can share the medium by using a dynamic allocation or static allocation. Static allocation is meaning like something is scheduled. Okay. So today is 14. So number 4 start and 5, 6, 7, 8, 9, 10 and sequentially. Okay. Something like this, something like a lattice schedule. That is static allocation. Dynamic allocation, okay. Who want to talk? Everybody raise a hand. Okay, whoever raised it first, then you go. Then who want to talk first? And you go. That is dynamic allocation. Then you can start talking. And in this case, we are assuming a single channel available. In reality, the multiple channels are available, but even multiple channels available, if you're going to deeper and deeper, in simpler problem, always assume there is a single channel available. Okay, time is continuous or slotted. We're going to talk about what is continuous. We know what the continuous. What we are talking is continuous talking. Slotted meaning, so we divide the time. We divided the time to the small buckets. Okay, so whenever there is bucket, there is people start. They have to wait until the bucket starts. Okay, so that is slotted concept. We're going to talk about detail. And carrier sense meaning, who want to talk? Okay, if I'm an old back, I want to talk, but someone is talking, then I'm solid. Meaning carrier sense. If someone is not talking, I carrier sense. I sense, then I can speak. Carrier sense. Well, I want to talk, but someone is talking now, so I'm carrier sense as a busy. The waiting for his speaking is done, then I can start. That is carrier sensing. Collision detection meaning if I am talking and the other person starts talking at the same time while I'm talking, there is collision. The receiver cannot receive properly. Okay, that is collision detection. So MAC protocol is famous. The pure Aloha. Aloha is to say Aloha. Why is that? It's a name. This Aloha concept protocol is developed by the University of Hawaii, and they named their paper as Aloha. And everybody starting to the Aloha, and that protocol started from University of Hawaii. Then this protocol named Aloha. We have Aloha, pure Aloha, which using the continuous time, and there's a slotted Aloha concept, and we call the slotted Aloha. all 802.11 wireless, your Wi-Fi is based on these ALHOA concept, and CSMA is carrier sense multiple access, meaning before I'm talk, I sense the carrier, like we are doing in the classroom. Before I talk, I sense the voice. If it is not busy, I can start talking. And there is a collision resolution algorithm. If something bad happened, I have to have some mechanism to overcome that. That is collision resolution algorithm. Then we're going to talk about this. Okay. So can you see the slide number 4? This is example of the continuous time, no collision detection, no carrier sense. I have 5 users, A, B, C, D, E. Over time, they are speaking their own messages. They don't have carrier sense, so they are very prone to error, and there is no collision detection mechanism, and the time is continuous time. Therefore, the E's first slide is successful. The D's first is not successful because of this collision. And this collision, this collide. This collide. Okay, this is good. This is good. This is good. This is not good. So only 4 packets are delivered properly. Do you see why? Do you see the 4 packets were successfully delivered? Do you see the 4 packets?
Yeah, we see it.
Okay, thank you. Why is that X packets are not delivered properly? Because while someone is talking, then the other is also talking, then collision happens. So no mechanism of the collision detection, no mechanism of carrier sense, meaning your information is not delivered properly. Okay, we have to have some solution for this in a wireless communication. Okay. Rather than static information, we want to have dynamic information. Why is the dynamic is better than a static? Okay, I'm gonna ask Jungmin and Yoon, why the dynamic is better than a static? No, no clue. So you understand what is dynamic and what is a static? Static is already scheduled. Okay. So from the left to the right, you can speak. And when you are done, the second guy speak. When you are done, and third guy speak. Dynamic is who want to talk first? And you first, then who want to speak again? Then dynamic. And that is dynamic and static. Because of conflicts. Okay, good try. Don't worry about your wrong answer.
Or maybe we can implement a buffer, because packets don't arrive like right at the same time.
Mm-hmm.
So maybe you can make a buffer that will just sequence them.
So you are buffering the collided packets.
What again?
You are buffering collided packets. How does it help?
Yes.
How does it help? Your packets already.
So for example, first the first packet from E comes, and then the packet from D comes, and then it's getting processed, and then the next one is the packet from C. So since the receiver is busy, we put C in the buffer.
Oh, okay. Okay. Let's clarify the problem. So in this case, there was only one receiver and 5 senders. One receiver and 5 senders. While D is talking and C is interrupted, meaning this packet is not deliverable because C started talking at the same time. Clear? So D started first, but in the middle of D speaking, C started. Then D's communication not delivered, C's communication not delivered because 2 packets are collided. On the receiver's perception, so he is sending 10110010, but in the middle, the one is not 1, 0 is not 1, it's contaminated. Because C star is on 10110110, right? The two signals are overlap over the air, the receiver has no ability to decode it properly. Clear? Is it Chanara?
Yeah.
Right.
Yeah. Then all of them, they should wait for like a green light or something from the receiver.
Okay, good point. So so my question to the Yeon and Jungmin was what is better to the dynamic or static? So we always want to have dynamic, because if we have a static, the inner loop guys can enjoy the network better than newcomers. So if you think about the Wi-Fi, there's always new guys in the town. So I want to have a given equal opportunity, everyone who want to talk to me, talk to my AP. That we call the QoS, quality of the service. And when we are giving you a quality of service, we always guarantee the fairness. Fairness meaning whoever want to connect to the internet via me will have fair chances of the network connection. Rather than who's close, who's coming first, who's louder. Okay, don't do that. You are all equal. I'm giving you equal opportunity to everybody. That's the concept of QoS, quality of the service. And we talked about fairness, F-A-R-R-N-E-S, fairness. Okay, so for the dynamic, everybody's fair. Whoever raised first, okay, you go first. Then you go, then you go. But competition period is given to fairly to everybody. Then everybody vote and raise their hand, then pick them. That is a fairness. How about the scheduled one, static? Okay, from there, whenever all this digestion is done, then newcomers I'll think about again. You have to wait for a long time. So it is unfair to some users. So Wi-Fi is completely based on the competition based. Something like LTE given in a static. Why the LTE and Wi-Fi is different? Wi-Fi is free. Whoever connected to me is connected. LTE, I have to guarantee some connection, right? Even in the worst case. I want to have my internet connection. I want to have my phone call. Even you have multiple guys there. So an LTE, I'm guaranteeing. Wi-Fi, there's no guarantee. If you can use more. The Wi-Fi, the LTE, you can always have a guarantee. So that is even you are in worst condition, the LTE is more reliable than Wi-Fi. Okay. So I'm jumping to the slide number 5. So assumption of the pure Aloha. So new arrival packets and each host transmitted immediately, meaning if I have something to say, I'm always to speak. Okay, I want to speak now. I don't have wait, and I want to speak again. Okay, so we call arrivals are Poisson with a total rate of lambda. You know, I'm assuming you know the Poisson distribution. Okay, we're gonna review the Poisson distribution in the next slide, but I assume you know the concept of Poisson distribution. So whenever we talked about the network, we usually assume the arrival rate is Poisson distribution. So if a packet is involved in collision, it is retransmitted after a random period of time. Those become backlog, meaning after I try something, after I try to say something, if it failed, I have to retransmit, right? But I'm not just speaking again right after my failure, but I'm waiting for some time, then I speak. That is much helpful. I'm going to show you why it is. And that concept is backlog. I'm backlogged and speak again, okay? And receiver provides the feedback on the received packet to implement collision detection, okay? So if I receive the ACK properly, meaning my packet is delivered properly. If not, I don't receive, meaning I'm waiting for my timeout, or sometimes I can have neg. Neg is negation of acknowledgement, meaning that packet wasn't delivered properly, okay? And there's no buffering. A backlog node does not buffer any new arriving packets. So I have something to say. Before I talk to this, I'm not receiving. Okay, or set of nodes accessing the medium is infinite. So I can retransmit it until I'm giving up. Giving up time is usually 7 times is practical, but in theoretically there is no giving up time specified. So from this Poisson distribution, I'm going to start from this Poisson distribution in next Monday's class. Okay, so I'm gonna pause in here. Any question about the class? I'm going to cover this Poisson distribution in next lecture. Any question? No. So,
So
whenever I ask a question, I know. Yep. Go ahead.
Oh, sorry, Professor. The midterm will include this lecture as well, right? Excluding Poisson.
Yeah, until I'm covered.
Oh, okay.
Yep. Because midterm is not challenging you, but it's somehow challenging. It's not. It won't be difficult. It's more like a time attack. Okay, don't worry too much. It is because it is a handout. Take a list very close to the take-home exam.